Hi, I'm Sophia, and this is part 2 of Modernizing Traditional Apps for Java Developers. In part 1, I covered what makes up a traditional app and why migrating to Docker makes sense. When containerizing an application, it might be tempting to refactor, re-architect, or upgrade it at the same time. However, a lift and shift approach is recommended where the application is first containerized exactly as is, with the minimal amount of changes possible. The application can then be regression tested and operationalized with Docker EE deployment pipeline. Some rules of thumb are 1. Keep the existing application architecture. 2. Keep the same versions of the OS and components and the application. And 3. Keep the deployment simple, static, and not elastic. Once the application is containerized, it will be then much easier and faster to change. For example, you are able to upgrade to a new version of the application server. You can refactor to microservices architecture, or dynamically scalable or elastic deployment. In this part, we'll dive into the code and migrate it from a traditional method of generating a package such as a WAR file and deploying it to an application server. We'll also show how to use Docker alongside CICD pipelines such as Jenkins. I'll show how developers can continue to use the IDEs that they are familiar with, but use Docker to build and run for consistency. So let's get started. The application is available on GitHub if you want to follow along. It's a typical Java web application. It's a servlet running on an application server that can read and write to a database. It utilizes a model view controller design where the data model uses Hibernate to manage the data entities, and the database transactions. Spring provides the framework for the controller, and the front-end view uses Java server pages for the user interface. The project uses Maven to automate builds, and it also makes it simple to import the code and dependencies into your favorite IDE. In practice, I would import the code into Eclipse and debug the code from there. However, if I just want to deploy and test out the code, I can write a simple script to do that as long as all the dependencies are available locally. I can use Docker to build the application and deploy it using a Docker file with a multi-stage build. Multi-stage builds use a separate container to compile and package the code into a WAR file. The first part of the Docker file uses a Maven container. The code and the POM file is copied to the container, which is used to resolve all the application dependencies. Maven compiles the code and packages it into a WAR file, which is held in an intermediate container. The second part of the Docker file uses a Tomcat container and copies the configuration files and WAR file from the intermediate Maven container. This produces the final container with the Tomcat and the application in the web apps directory. To test the application, I have a MySQL instance running with a database and tables already created. Later, I'll create a Docker file to create a container with MySQL and the database. Start the application Docker and open the web page to check it out. A continuous integration, continuous delivery platform uses different systems within an organization to automatically build, deploy, and test application. This section discusses a typical CICD workflow using Docker EE and the interactions with those repositories that are shown in the following illustration. A typical CICD workflow follows these steps. First, build the application. A change to the version control of the application triggers a build by the CI agent. A build container is started and passed parameters specific to the application, and the container can run on a separate Docker host or on UCP. The container obtains the source code from version control and runs the command of the application's build tool, and finally pushes the resulting artifact to a repository manager. Second part is the build image. The CI agent pulls the Docker file and associated files to build the image from version control. The Docker file is set up so that the artifact built in the previous step is copied into the image, and the resulting image is pushed into Docker Trusted Registry. If Docker Content Trust has been enabled and Notary has been installed, the image is signed with a CI/CD signature. The third part is to deploy the application. The CI agent can pull a runtime configuration from version control using Docker Compose YAML and environment-specific configuration files, and use them to deploy the application onto the universal control plane of Docker EE via the CLI-based access. And finally, testing the application. The CI agent deploys a test container to test the application deployed in the previous step, and if all the tests pass, then the image can be signed with a QA signature by pulling and pushing the imager to Docker Trusted Registry. The push triggers the operations workflow. Docker Trusted Registry. If the application is at the end of its life and only requires maintenance or security patches, it can be maintained in the Docker Trusted Registry without a CI/CD. Docker Trusted Registry is how I can publicly share images, but I also have control over how the image is shared and made available. My account is in the admin group, so I can push and pull both app and database images. Docker Image LS tells me what images I have locally, and to push the image to the registry, I need to give it a tag which matches the registry setup. Docker Image Tag adds a new name to the existing image. This is a full image tag which has the registry domain, the repository domain, the image name, and a version number. Now, I need to authenticate with Docker Login using my credentials for DTR, and to upload the image, I run Docker Image Push using the new tag. When all the layers have uploaded, I can see the image listed in the Docker Trusted Registry, and now that it's available to download and run in another environment. This is going to be a test environment, so I'll pull a database image so I can run my MySQL in a container as well. I won't start the individual containers though. I have a Docker Compose file, which I'll use to start the whole application. Docker Compose is a tool for defining multi-container applications, configuring them with the same options you use when you run containers in production. I have database definition here and a web app here. To start the whole app, I run Docker Compose up-d and to start both containers in the background, and that's it. My app is deployed to the test environment now, and back on my laptop, I can browse to the VM in the cloud and use the app. This app is using exactly the same Docker images, so the behavior is the same as when I run it locally. That's how the deployment process works in Docker. You build the image, push it to registry, then use the same image to run your app in different environments. When you deploy your app to production, you're running a container from an image that's been tested and approved in all the QA environments. The image I'm using as a base for my app is a public image with Tomcat already configured. The only way to apply updates to an app running in a container is to build a new image from the latest base image, then replace the container with your new container from the new image. My app is currently based on Tomcat 6, and if I check Docker Hub, there's a later version available. The version will have hotfixes and security patches, so to update Tomcat, I just change the from line in the Docker file to use the latest tag, then build the image. I'll use the same image name so I can push this image up to my DTR directory, but I'll use a different version number in the tag. The very first instruction in the Docker file is changed, so that breaks the cache for the rest of the layers, and Docker will execute all the instructions in the build. When it completes, I push the image in the same way, and here's how it looks in the DTR, the same repository but a new version of the app. To update my test environment, all I need to do is change the image version in the Docker Compose file, specifying version 2 instead of version 1. Now I can repeat the Docker Compose up command. Docker Compose checks the desired state in the Compose file against the containers which are currently running. I see database definition is unchanged, so it leaves the container running, but the web app definition has changed, so it stops the current container and starts a new one. This is the update procedure you have when you have a single server running apps in Docker. It's fast, simple, and safe, and it's easy to automate in a continuous deployment pipeline, so there are no manual steps to deploy application updates or Windows updates. Using a single server does mean some downtime while the app is updated. In the few seconds that the old container stopped and the new one started, there's nothing running to process requests, but Docker supports zero downtime updates in high availability environments, where you have multiple servers running in cluster, and I'll show you that soon. So to recap, Docker can simplify the build and deployment process through increasing the density of application servers on hardware to allow more efficient horizontal scaling. It can improve security by applying patches to containers and let your organization realize significant gains in cost savings. In the next section, I'll explore what you can do to further modernize your application, including moving it towards a modern microservices architecture and using polyglot development. And if you want to get started modernizing your own app, head to Play with Docker, a training site which is an online environment with Docker configured that has a lot of great tutorials. If you want us to help you modernize your application suite, head to docker.com/MTA to learn how we partner a Docker architect with an infrastructure provider such as Microsoft or Accenture to bring your apps into the modern world.